Okay, I'd like to tell you about Gauss's law here. Gauss's law is for finding electric fields, and this is how you do it. You take advantage of the fact that we have two equations for finding the flux inside that passes through a closed surface. So the electric flux that passes through a closed surface can be found either by adding up all the charges enclosed by the surface and dividing by a constant. So that's the easy way of finding it, usually, is just add up all the different charges that are enclosed and then divide by a constant, epsilon naught. Or you can you can find the electric flux through a closed surface by adding up all of the electric fields on the Gaussian surface dot dA, the dAs of the Gaussian surface. Let me add some subscripts here for the E. This E, when you want to find the flux through a closed surface, this electric field is not just the electric field any place. This is the electric field on the surface of the thing you're trying to find the flux through. That's going to be called the Gaussian surface. So this is the E on the Gaussian surface. In honor of Gauss. And these dAs, they make up the Gaussian surface. And what this is saying, this right here, if you have that there, you don't need parameters. It's saying what you're going to do is where you begin and where you end your integral is you just start somewhere on that surface and you keep adding until you've added every single E dot dA for the entire surface. So this is a definite integral, and what makes it a definite integral is this symbol here. This is called a closed surface integral. When you see that circle, you have a closed surface integral. It means add up the entire surface E dot dAs for the entire surface. Okay, so what Gauss's law then does is it just takes those and puts them together, since they're both finding the flux through a closed surface. This is how you see Gauss's law stated sometimes. You see it saying Q enclosed, the total charge enclosed, over epsilon naught. That is going to be equal to the electric field, the net flux through a closed surface, E dot dA. And remember, this is the E at the Gaussian surface. And this is the dA of the Gaussian surface. And this is a dot product here, and these are vector quantities. Okay, now why does this help us? How does this help us find the electric field? Well, you see that if we can fill in the blanks here, what will be left over in here is there's an electric field. So if we know this is a constant. If we know that and that, we can just solve for E. So let me show you how this works. Let's use this equation to find the electric field due to a point charge. Now we already know the electric field due to a point charge, but let's pretend like we don't know it. So here's a point charge Q. And as you might guess, there's electric field lines going out in all directions here. And I'm only drawing them in the plane of the paper, but they're, one's coming out towards you, one's going out this way. Okay, they're going out in all directions. And if I want to know the electric field, say here, what you do is you draw a Gaussian surface that passes through there. And if you draw the right Gaussian surface, then you have a lot of nice cancellation. So that's a Gaussian surface. It's an imaginary surface, but notice that it passes through the point that I want to know the electric field for. So I want to know the electric field right there. Okay, well, if that's the case, now let's write down Gauss's law. It says that the Q enclosed, which is, this is the Q that's enclosed, so I'll make a capital Q since it's all enclosed, over epsilon naught. That's equal to the closed surface integral of E dot dA. All right, now I'm running out of space here, so I'm going to put this right here then. Okay, yeah, I'll put it like this. All right, so it turns out that the charge enclosed over epsilon naught, I'm done with that side. That side's completely done. But let's take a look at, if you notice that the E and the dA are always in the same direction. So let me draw you some dAs. Here's a dA. It's pointing this way. I'm making that look a lot bigger than it is. dA is infinitesimally small, but it's pointing normally out of the surface, or perpendicularly out of the surface. And so is the E right here. The E is going to be going this way. And so E and dA are parallel to one another. Same thing with right here. Here's your E, or here's your dA, and here's your E. And they're parallel to one another. And let's just do one more. Here's your dA. That's the little area dA. And the E is this way. And so they're parallel to one another. And so if you notice then, I can get rid of the dot product. I'm going to say I'm going to get rid of this dot product. And the argument I'm going to give, Q enclosed, well, it's just all Q, over epsilon naught. And I'm going to go to this. It's just E dA. And the argument for that is because E is perpendicular, E is perpendicular to dA at each point on the Gaussian surface. Okay, so I just got rid of the dot product, and you know what? You'll do that every single time. For every one, you're going to have to figure out how to get rid of the dot product. Okay. The next one is, since E is the same at every location on here, it doesn't change. We say E is uniform at all points on the Gaussian surface. I'm not saying E is uniform. I'm saying E is the same at every point on the Gaussian surface, not just anywhere you want to go. And because of that, you can pull E out of the integral. So what we're going to do is we're going to say Q over epsilon naught is equal to, I pull E out of the integral, and I'm left with this. Okay, well, the argument for that then is I did that because E is uniform at all points on the Gaussian surface. Okay, well now this is saying just sum up all the dAs. Well, if I sum up all the dAs, I get the area of a sphere, surface area of a sphere, which is 4 pi r squared. And if I bring this on the other side, I get E is equal to Q over 4 pi epsilon naught r squared. Hey, but 1 over 4 pi epsilon naught, that right there is K. So I just used Gauss's law to derive something that we already knew, but it's much more powerful than that.